Right. Hi, everybody. Here's question 67 from Chapter 6. This is a thermal equilibrium problem between a wafer of pure gold and some water into which it's submerged. We're given, first we're promised that the container is insulated, meaning that the system is isolated and there's no heat exchange with the surroundings of the water. So that is important once you get into physical chemistry, I suppose. These are always some sort of problem where the negative heat of one thing equals the heat of the other thing, and you set these up with mass times specific heat capacities and changes of temperature between the two of them, right? With one negative and the other positive, and then you solve for either the initial or the final temperature values, and that's usually how these things pan out. This one is a binary system. This can also be done with three species in the system, as we'll see later. Okay, so in this case, though, we have gold and water. So let's get ourselves set up with negative heat of gold. We'll put the gold as the negative value. All right, has to become equal to the heat of the water for there to be a thermal equilibrium achieved. All right, so now we start plugging in our equation. So this is going to be the mass of the gold times the heat capacity of the gold times the change in temperature of the gold equal to the same of the water. Right, and I'm sure you've seen 10 billion of these setups already. Okay, so now let's start sticking some values in this stuff. Okay, so 31.1 grams. All right, times heat capacities you have to get from table values. Or experimental data, either or. Okay, joules per degree Celsius per gram. Okay, times delta T equals, how much water was there? 64.2. 2 grams times 4.184 joules per degree Celsius gram times delta T. Okay. So this gives us negative 3.908. Oops, excuse me, 9808. Times T1 of the gold. Actually, you know what? Let's just put the value in for that. Gold was initially at 69.3 degrees Celsius. 69.3 degrees Celsius. This one is some unknown temperature. It is T2 that we're after. We want the temperature at which they achieve this equilibrium value. Okay, and then for the water, we have 68.613. T2 is again unknown. And this started at 27.8 degrees Celsius. Okay, so in all of these problems, what you end up with is you'll have some factor of T2 and then some factor of degrees Celsius, and you isolate your degrees Celsius on one side and the T2s on the other side, and then you divide the degrees Celsius side by the coefficient of T2 once you finish solving your values here. So I think I'll take this one more step, and then after that we'll skip to the good stuff. 108 T2 plus 275.869. All right, and this is degrees Celsius. This is the gold side solved. And then here we're going to have 268.613 T2 minus 1,467.44 degrees Celsius. All right, that's the water side taken care of. Okay, so we'll group the one on the other side. So T2 would be equal to in this side, this is 275 plus that, because this is going to be moving, this would be moving to the other side. So 275.869 degrees Celsius plus 7467.44 degrees Celsius. We would be dividing that by the sum of these two values here. So this is 268. Let's try that again. 268.613 plus 3.9808. Right, and you see this is going to give you some result in degrees Celsius. And that sum result is 28.4. There you have it.